Past the last visible star, past the faint smear of the farthest galaxy any telescope has ever caught, there is a place where the universe simply stops answering. Not a wall. Not a fence. Not a curtain of black glass holding back some cosmic ocean. Something stranger. Something that has taken the best minds of the last century to even begin to describe, and which still, after all the equations and all the satellites and all the photographs of the infant cosmos, refuses to resolve into a picture the human mind finds comfortable. The instinct is always to picture an edge. That instinct is simply how a mind built by 3 billion years of evolution on the surface of a finite planet is wired to think. Every object ever touched has a boundary. Every room has a wall. Every ocean has a shore. Human intuition for what space means was assembled from a life spent inside boxes, inside rooms, inside a body with a skin that separates inside from outside. So the question of what lies at the edge of the universe gets asked the only way the mind knows how to ask it, and that is precisely the problem. The universe was not built for the comfort of that intuition. Here is what is actually known, and it is worth sitting with for a moment before going further, because it is one of the strangest and most hard-won facts our species has ever assembled. Roughly 13.8 billion years ago, everything, every atom that would one day become a star, a planet, a bird, a thought, was compressed into a state so dense, so violently hot, that the very language of physics starts to buckle when describing it. Not a point in space, as popular imagination likes to render it, but the birth of space itself. Time began ticking. Distance began meaning something. And from that instant, the fabric of reality has been stretching outward in every direction at once, carrying galaxies away from one another like raisins in a rising loaf of bread, dragging the light of ancient stars across gulfs so vast that the numbers stop feeling like numbers and start feeling like a kind of poetry. This expansion has been mapped with extraordinary precision. The afterglow of creation itself has been read, a faint microwave hiss that still bathes every corner of space, the fossilized echo of the moment the universe first became transparent to light. The biography of the cosmos has been reconstructed, almost month by month, from its first fraction of a second to this exact moment. This is not speculation. This is some of the most rigorously tested science human beings have ever produced. And yet none of it, not one instrument, not one equation, has ever shown a genuine edge. Ask an astrophysicist what lies beyond the last galaxy anyone can see, and the answer will not be a shrug. It will be one of 4 entirely different answers, each backed by real mathematics, each terrifying and beautiful in its own way, and each one utterly incompatible with the picture of a cosmic aquarium with glass walls holding back an infinite darkness outside. One answer says there is no beyond, because traveling in a perfectly straight line for long enough would eventually lead back to the starting point, circling the entirety of existence the way an ant circles the surface of a ball. Another says the edge is not a place at all, but a moment, a boundary not in space but in time, where the universe as it currently exists gives way to something still being born, an ocean of raw creation that has never stopped expanding since the beginning. A third says that what looks like an edge is only the limit of what light has had time to reveal, and that beyond it, indifferent to human ignorance, galaxies continue to burn exactly as they do here, forever out of reach. And a fourth, the strangest of all, suggests that this entire universe might be a single bubble adrift in a boiling froth of others, each one operating under different laws, different constants, perhaps even a different number of dimensions, and that the edge of this universe is the edge of physics itself, a membrane beyond which the very rules holding atoms together simply cease to apply. 4 answers. 4 different shapes for infinity. And remarkably, modern cosmology cannot yet say with certainty which one is true, or whether the true answer is some combination not yet fully imagined by anyone. What follows is a walk through each of these possibilities with the seriousness they deserve, not by throwing equations at the problem, but by building the intuitions, one at a time, that let these ideas actually be felt rather than merely memorized. Because the story of the edge of the universe is not really a story about distant galaxies at all. It is a story about the strange, humbling architecture of the human mind trying to comprehend something built on a scale it was never designed to hold. Let us begin with the simplest of the 4 answers, because it is also the one most often mistaken for the truth, and untangling that mistake teaches us something essential about everything that follows. Picture a man standing alone in an open field at the deepest hour of night. No moon. No city glow on the horizon. Just black sky pressing down in every direction, and in his hand, a single lit lantern. The lantern throws a circle of light perhaps 30 meters across. Beyond that circle, there is nothing he can see, not because nothing exists there, but because his light has not reached that far. Now ask him, where does the field end? If he is being honest, he will admit he has no idea. He can describe exactly where his light ends. He can describe, with total confidence, the grass illuminated at his feet, the shape of a fence post 15 meters to his left, the texture of the ground where his lantern's glow fades into shadow. But the field itself might continue for another kilometer beyond his circle of light, or 10 kilometers, or it might, for all his lantern can tell him, extend forever. His instrument has a range. The field does not necessarily share that range. Confusing the edge of his light with the edge of the world would be, quite simply, a mistake of perspective, an understandable one, perhaps even an inevitable one, but a mistake nonetheless. This is not a metaphor invented for convenience. It is, almost exactly, the situation every human being finds themselves in every single night they look up at the sky. Light is fast, staggeringly fast, nearly 300,000 kilometers every second, fast enough to circle the Earth 7.5 times within the span of a single blink. But the universe is vast on a scale that makes even that speed feel almost sluggish. And crucially, light is not infinitely fast. It takes time to travel. Time that can be measured. Time that means every single photon striking any retina, from every star, every planet, every glowing cloud of interstellar gas, is not showing the present. It is showing the past, sometimes the recent past, sometimes a past so distant that the object which emitted that light may no longer even exist in the form being observed. A glance at the sun shows it as it was a little over 8 minutes ago. A glance at the nearest star beyond our own shows it 4 years into the past. When telescopes strain to catch the faintest, most distant galaxies ever photographed, they are looking back not thousands or millions, but billions of years, capturing light that left its source when the universe itself was a fraction of its current age, light that has been traveling, uninterrupted, ever since, just to reach a mirror on Earth at this precise moment. This creates something cosmologists call the observable universe, and understanding what that phrase actually means, rather than what it sounds like it means, dissolves an enormous amount of confusion. The observable universe is not the entire universe. It is the portion of the universe from which light has had enough time to reach us since the beginning of everything. It is the man's lantern circle, except instead of 30 meters, the radius of our circle, accounting for the fact that space itself has been stretching this entire time, carrying those ancient light sources even farther away while their light was in transit toward us, comes out to approximately 46 billion light years in every direction. 46 billion. Not 13.8 billion, which might seem like the more intuitive number given the age of the universe. That gap exists precisely because space has not been sitting still while the light traveled. It has been expanding the whole time, dragging the source of that ancient light further away even as its glow raced toward us. The math is subtle, but the concept is not. Our field is not merely large. It has been getting larger the entire time we've been trying to measure it. And here is the crucial point, the one that reframes the entire question of a cosmic edge. The 46 billion light-year boundary of our observable universe is not a wall. It is not the edge of matter. It is the edge of our knowledge. Beyond it, and there is no serious reason to doubt this, stars continue to ignite, galaxies continue to spiral, entire clusters of matter carry on their business completely indifferent to the fact that no signal from their activity has yet reached any instrument on Earth, and by the accelerating expansion of space, some of it never will. This is worth pausing on, because it carries an emotional weight easy to rush past. There may be a galaxy, at this very moment, undergoing some spectacular transformation, a supernova brighter than a billion suns, the birth of a black hole, the slow collision of two spiral galaxies locked in a gravitational embrace that will last hundreds of millions of years, and it is possible, even likely, that we will never know. Not because the event is too far to eventually see, but because the space between us and it is stretching faster than light can cross it. The information is permanently, physically unreachable. Not hidden. Not encrypted. Simply outrun by the very fabric it would need to travel through. So when someone points at the outermost boundary of what our telescopes can detect and calls it the edge of the universe, they are technically correct only in the narrowest sense, the edge of what light has managed to deliver to our doorstep in 13.8 billion years. It is a beautifully precise number, one of the great triumphs of observational science. But it describes the limits of the observer, not the limits of the observed. The man in the field, if he is wise, does not conclude that the world ends where his lantern's light fades. He simply acknowledges the boundary of his own vision and begins to ask a more interesting question. If I cannot see past this point, what tools, not of light, but of reason, of mathematics, of inference, might let me understand what continues beyond it? That question is where cosmology stops being merely descriptive and becomes something closer to detective work. And it is where our exploration must go next, because the moment we accept that the horizon of light is not the edge of reality, an entirely new and far stranger set of possibilities opens up. Possibilities that do not require us to see anything at all, only to trust the deep structure of the mathematics that has, again and again, described our universe with uncanny accuracy. To appreciate how strange and how recent this understanding actually is, it helps to remember that for the overwhelming majority of human history, the very premise behind the question would have seemed absurd in the opposite direction. Ancient civilizations did not typically wonder whether the universe had an edge because they did not typically conceive of a universe large enough for the question to feel urgent. The night sky, to most of our ancestors, was not an infinite abyss but a kind of ceiling, a dome, often literally imagined as a solid vault, studded with fixed points of light, rotating serenely above a flat or gently curved earth. The Babylonians pictured a firmament, a hammered metal dome separating the waters above from the world below. Ancient Egyptian cosmology described the sky as the body of a goddess arched protectively over the earth. Aristotle, whose physics dominated Western thought for nearly 2,000 years, proposed a series of nested, crystalline celestial spheres, each carrying a planet or the fixed stars, all of them bounded by an outermost sphere beyond which, by definition, nothing existed at all, not even empty space, since space itself was considered a property of the cosmos rather than a container it sat within. In this sense, ancient thinkers had an easier time answering our question than we do today, precisely because their universe was small enough, and their cosmology confident enough, to simply assert an edge and stop there. The outermost celestial sphere was the edge. Beyond it, nothing, not even nothingness, because the very concept of beyond required a where, and there was no where left to be beyond. It took an extraordinary, centuries-long unraveling to dismantle this comfortable picture. Copernicus displaced the Earth from the center. Galileo's telescope revealed moons around Jupiter and mountains on our own moon, proving the heavens were not perfect, unchanging crystalline shells but were made of the same kind of ordinary matter found underfoot. Newton described gravity as a universal force acting the same way on falling apples and orbiting planets, dissolving the ancient distinction between the corruptible earthly realm and the perfect celestial one. And then, in the early 20th century, came the discovery that would make the ancient question of a bounded, static cosmos not merely outdated but fundamentally incoherent. The universe was not sitting still at all. It was expanding. The astronomer Edwin Hubble, working through the 1920s with painstaking observations of distant galaxies, objects that, remarkably, were not even confirmed to lie beyond our own Milky Way until just a few years earlier, discovered something that should have seemed impossible under the prevailing assumptions of the time. Nearly every galaxy he examined was moving away from us. Not randomly, not scattered evenly between approaching and receding, but overwhelmingly, systematically retreating, and retreating faster the farther away they were. This single observation, simple to state but staggering in its implications, forced physicists to confront a universe that was not the fixed, eternal backdrop it had always been assumed to be, but something dynamic, something with a history, a trajectory, and, working the observation backward through time like rewinding a film, an apparent beginning. If everything is moving apart now, then at some point in the past, everything must have been much closer together. Running the film back far enough arrives at a moment when all of it, every galaxy, every star, the entirety of what would become the observable universe, was compressed into an almost unimaginably small, dense, hot state. This is, of course, the origin of what came to be called, somewhat dismissively at first by a rival scientist who intended the name as mockery, the Big Bang, a term that has stuck despite being, in some ways, a slightly misleading label, since it conjures an image of an explosion happening at a specific point within a pre-existing empty space, hurling matter outward into that emptiness. This is not quite what current cosmology describes. There was no pre-existing empty space for anything to explode into. Space itself, along with time, began at that moment. The Big Bang was not an explosion in space. It was the beginning of space. This distinction matters enormously for our central question, because it immediately forecloses one of the most common intuitive pictures people carry, the idea of the universe as a sphere of matter expanding outward into a surrounding void, like a balloon inflating within a room. There is, according to virtually every serious cosmological model, no surrounding room. There is no exterior void waiting to receive the expanding universe. The expansion is not the universe moving into space. It is space itself increasing, the very substrate of distance and location growing more voluminous, carrying the matter embedded within it apart as a passive consequence. The image of a rising loaf of raisin bread, used earlier, deserves a slightly closer look here because it captures this distinction better than almost any other common analogy. As the dough rises, every raisin moves farther away from every other raisin. But no individual raisin is traveling through the dough toward some destination. The raisins themselves stay put, relative to their immediate surroundings. It is the dough between them that is expanding, carrying them apart as a consequence of its own growth. A sufficiently small, sufficiently curious observer living on the surface of one particular raisin would observe every other raisin receding. And, crucially, this would be true no matter which raisin that observer happened to be standing on. There is no special, central raisin from which all the others are fleeing. Every point sees every other point receding, symmetrically, which is exactly what astronomers observe when they look at the galaxies surrounding our own, a universe with no discernible center, expanding uniformly from every vantage point simultaneously. This has a subtle but important consequence for the shape of our earlier lantern analogy. The man standing in the dark field with his lantern is not merely limited by the speed at which his light travels outward. He is also standing on ground that is itself stretching, continuously, in every direction, even as his light attempts to cross it. This is why the true radius of the observable universe, 46 billion light-years, is so much larger than the 13.8 billion years that have actually elapsed since the beginning. The light left its source long ago, but the source itself has continued receding, carried by the stretching of space, throughout the entire multi-billion-year journey that light has been making toward us. By the time that ancient light finally reaches an eye or a telescope on Earth, the object that originally emitted it is no longer 46 billion light-years away in the sense of, that is how far the light traveled. It is 46 billion light-years away right now, at this very moment, having been carried further outward by the relentless stretching of the space between us during the entire multi-billion-year transit. It is a genuinely dizzying fact, and it is worth restating plainly. Some of the most distant galaxies visible in deep-field images taken by modern telescopes are showing light that left them when the universe was less than 1 billion years old, light that has been traveling, uninterrupted, for well over 13 billion years. And yet, because of the expansion that has occurred during that entire journey, the actual galaxy that emitted that light, if its position could somehow be measured this instant, would now be located more than 30 billion light-years away, far beyond the distance the light itself has nominally traveled. Looking at distant galaxies is not just looking backward in time. It is looking at objects whose current location has continued to recede throughout the entire journey their ancient light has been making. This is the honest, rigorously supported foundation beneath the lantern in the field analogy from earlier, and it is worth returning to it now with this added layer of nuance. The boundary of the observable universe is not simply the distance light could travel in the time available. It is the distance to where a source now sits, having been carried outward by cosmic expansion for the entire duration that its ancient light has spent crossing the gap toward us. It is, in a very real sense, a horizon shaped jointly by two separate forces, the finite speed of light and the ceaseless stretching of the medium that light must cross. And this brings us to perhaps the most important reframing of the entire discussion. The observable universe's boundary is not a fixed thing waiting patiently for us to eventually reach it. It is, in a strange sense, retreating from us even as we speak, not because the universe is shrinking, but because the accelerating expansion of space means that more and more distant regions are crossing the threshold beyond which their light can never reach us at all. Every year that passes, a small number of galaxies that were once, in principle, capable of eventually sending us a signal cross over into permanent causal isolation, their light forever outpaced by the stretching of the space between us. Our observable universe, our lantern circle of light, is not merely finite. In a cosmological sense, its boundary is subtly but continuously being redrawn, isolating us more and more from the ever-expanding whole of which we are only ever able to witness a shrinking fraction. This is not a cause for despair, though it is, admittedly, difficult to sit with. It is simply the nature of the field we find ourselves standing in, vast beyond the reach of any single lantern, its true extent perhaps unknowable in principle, its boundaries defined not by where matter ends but by where light and causality themselves reach their absolute limits. If the light we can see has a boundary, but that boundary is not the boundary of reality itself, the next question becomes almost unavoidable. What if we could somehow travel past that boundary, not with light, but with some hypothetical vessel unconstrained by the ordinary limits of physics, some craft that could simply keep going, in a straight line, forever? What would it eventually find? General relativity, the theory Albert Einstein handed to the world just over a century ago and which has since passed every single experimental test thrown at it, offers an answer to this question that manages to be simultaneously more elegant and more disorienting than almost anything else in modern physics. And to understand it, we need to set aside, just for a moment, everything we assume about the word straight. Consider an ant. Not a metaphorical ant, an actual, ordinary ant, placed on the surface of a perfectly smooth, perfectly round globe, a planet with no mountains, no valleys, no horizon-blocking terrain of any kind. This ant has no concept of up towards space or down toward the planet's core. As far as its entire sensory experience is concerned, it exists on a flat, two-dimensional plane that happens to curve in ways too gentle and too vast for its tiny body to perceive. Now let the ant walk. It picks a direction, let's say due north, though on a sphere every direction is equally arbitrary, and it commits to walking in that direction, and only that direction, without ever turning, for the rest of its existence. What happens? If the globe were flat, if it were an infinite plane rather than a sphere, the ant would simply walk forever, receding into a horizon that always retreats exactly as fast as it advances, never arriving anywhere, never returning, never completing anything. But the globe is not flat. It curves. And because it curves in a consistent, closed way, something extraordinary happens to the ant's journey. Without ever changing direction, without ever turning around, the ant will eventually arrive back at the exact point where it started. It will have circumnavigated the entire surface of its world by doing nothing more than moving forward, in a straight line, the whole time. This is not a trick of perception. It is not an illusion born of the ant's limited senses. It is a genuine geometric fact about curved surfaces. On a sphere, a straight line, the shortest path between 2 points, what mathematicians call a geodesic, is not actually straight in the sense a flatlander would understand. It is a great circle. And every great circle, if followed long enough, returns to its origin. Crucially, the ant's world has no edge. At no point during its journey does it encounter a fence, a cliff, or a boundary marking the end of the surface. The ant could, in principle, walk for the rest of its life and never once hit a wall. And yet its world is not infinite either. It has a definite, measurable, finite surface area. The exact number of square meters of that globe's skin could be calculated precisely. The ant's world is finite, but it is unbounded. Finite in size. Infinite in the sense that there is no boundary anywhere within it that says this is the end. This single idea, finite yet unbounded, is one of the most powerful and most consistently misunderstood concepts to emerge from 20th century physics, and it was precisely this analogy that Stephen Hawking returned to again and again when trying to explain one of the possible large-scale shapes of the universe itself. Here is the leap, and it is a genuinely difficult one to hold in the mind, because it requires adding a dimension to an analogy already built around a two-dimensional creature living on a curved surface. If a two-dimensional surface, the skin of a sphere, can curve through a third dimension in a way completely invisible to the two-dimensional beings living on it, then it stands to reason, mathematically at least, that three-dimensional space itself could curve through some higher, fourth spatial dimension in a way completely invisible to the three-dimensional beings living inside it. We cannot picture this the way we can picture the ant's globe from the outside, hovering above it like a satellite. We are, in this analogy, permanently trapped inside the surface. We are the ant, not the observer looking down at the ant. But mathematics does not require us to visualize something in order to describe it with total rigor. The equations of general relativity allow for exactly this kind of universe, a closed, positively curved three-dimensional space, embedded, in a purely mathematical sense, within a four-dimensional structure we can never directly perceive, only calculate. If our universe possesses this kind of geometry, then the implications for our original question become startling. A hypothetical spacecraft, freed from every practical constraint, launched in a perfectly straight line and allowed to travel for an inconceivable span of time, not thousands of years, not millions, but a span so vast it would make the current age of the universe look like a single heartbeat, would never encounter an edge. It would never fall off the side of existence into some external void. Instead, having crossed a distance almost too large for numbers to hold meaning, it would eventually find itself arriving back at its point of departure, having circumnavigated the entire universe by doing nothing more than moving forward the whole time. In a universe shaped this way, asking what lies at the edge becomes a question as fundamentally malformed as asking what lies at the corner of a billiard ball. The question assumes a feature, an edge, a corner, that the geometry simply does not contain. It is not that the answer is hidden or unknown. It is that the question itself is built on a false premise, the same false premise the ant would be making if it insisted its world must have a border simply because every enclosed space it had ever previously experienced, a leaf, a stone, a crack in the pavement, happened to have one. Now, it must be said plainly and honestly, we do not currently know, with certainty, whether our universe actually has this kind of closed, positively curved geometry. The most precise measurements available to modern cosmology, drawn from that same ancient microwave afterglow mentioned earlier, suggest that the universe is remarkably close to flat, so close that current instruments cannot definitively rule out a very slight positive curvature, the kind that would only become apparent across distances vastly larger than even our 46 billion light-year observable horizon. It remains a live, serious possibility within the scientific literature, one actively debated and refined as measurements grow more precise with each passing year. But even as a possibility, its implications are worth sitting with, because it fundamentally dismantles the intuitive picture most people carry of a universe as some kind of expanding balloon with an inside and an outside, a contained volume pushing outward into some pre-existing emptiness. If the universe is closed in this way, there is no outside for it to push into. There is no boundary skin holding anything in. There is only the surface itself, vast beyond comprehension, curving back upon itself in a dimension we cannot see, complete, self-contained, and utterly without an edge. The ant on its globe never needed a wall to have a finite world. Perhaps neither do we. Before going further into the implications of a closed, curved cosmos, it is worth pausing to understand something that often goes unaddressed in casual treatments of this subject. Curvature, in the mathematical sense used by cosmologists, is not one single concept but a small family of related possibilities, and the differences between them lead to profoundly different destinies for the universe as a whole. Return once more to two-dimensional surfaces, since they remain the most reliable tool available for building intuition about something we cannot directly visualize in 3 dimensions. There are, broadly speaking, 3 distinct kinds of geometry a surface can possess, and each has an everyday object that captures its essential character. The first is positive curvature, the geometry of a sphere, the geometry of the ant's globe described earlier. On a positively curved surface, parallel lines, if extended far enough, eventually converge and cross. Consider 2 ants standing side by side at the equator of a globe, both facing due north, both walking in perfectly parallel lines according to their own local sense of straight. Despite starting parallel, despite never once turning, both ants will eventually meet at the North Pole. Their parallel paths converge, purely as a consequence of the surface's curvature, not because either ant chose to turn toward the other. Triangles drawn on such a surface also behave strangely. The 3 interior angles of a triangle drawn on a sphere always sum to more than 180 degrees, a fact easily verified by drawing a triangle connecting the North Pole to 2 points on the equator. Each of those 2 base angles is already 90 degrees on its own, before even accounting for the angle at the pole. The second is negative curvature, the geometry of a saddle, or the frilled, undulating edge of a lettuce leaf, or the shape mathematicians call a hyperbolic plane. On a negatively curved surface, parallel lines behave in precisely the opposite way. Rather than converging, they diverge, spreading apart from one another the farther they extend, never meeting, always increasing their separation. Triangles on such a surface have interior angles that sum to less than 180 degrees. A universe with this kind of geometry would be open and, in virtually every model that considers it, infinite in extent, a hyperbolic space stretching outward in every direction without any possibility of the kind of closure that would allow a traveler to circumnavigate it and return home. The third is zero curvature, flatness, in the ordinary, everyday sense of the word, the geometry of an infinite tabletop or an idealized sheet of paper extending in all directions. On a flat surface, parallel lines remain parallel forever, precisely maintaining their separation no matter how far they extend. Triangles behave exactly as taught in any school geometry class, their interior angles summing to precisely 180 degrees, no more, no less. This is the geometry most people unconsciously assume applies to the universe as a whole, largely because it is the geometry that governs everyday experience at human scales, where the curvature of even our own planet is too subtle to notice without specialized instruments. Now, the entire discussion of a closed universe returning a traveler to their starting point, presented earlier through the analogy of the ant on the globe, applies specifically and only to a universe with positive curvature, a universe shaped, in its large-scale 3-dimensional structure, like the 3-dimensional analog of a sphere's 2-dimensional surface, a shape mathematicians call a 3-sphere, or hypersphere. It is a genuinely difficult shape to picture directly, precisely because visualizing it properly requires imagining a 3-dimensional surface curving through a 4th spatial dimension, in exactly the way the 2-dimensional surface of an ordinary sphere curves through the 3rd dimension that its inhabitants can never directly perceive. But the underlying mathematics, while impossible to fully visualize, is entirely well-defined and has been worked with by physicists for over a century. If, instead, the universe possesses negative curvature, the saddle-shaped, hyperbolic geometry, then the picture changes dramatically. An open, negatively curved universe would almost certainly be infinite, and a hypothetical traveler moving in a straight line would never return to their starting point, would never circumnavigate anything, because the very structure of the space causes trajectories to diverge and spread apart rather than curve back upon themselves. This scenario shares more in common with the infinite, flat universe discussed elsewhere in this exploration than with the closed, finite cosmos of the sphere analogy, though the specific mathematical details of how space curves and spreads differ meaningfully between the two. And if the universe possesses exactly zero curvature, perfectly flat, in the geometric sense, then it occupies a kind of knife's-edge position between these two other possibilities. A perfectly flat universe could, in principle, still be finite, if it possessed some unusual global topology that wrapped back on itself in a way that did not require curvature in the traditional sense. The way a video game world can be built so that walking off the right edge of the screen causes a character to reappear on the left edge, a closed loop achieved through connectivity rather than curvature. Cosmologists have not ruled this out entirely, and there are ongoing observational efforts to detect the subtle signatures such a topology might leave in the patterns of the ancient microwave afterglow. But in the absence of any such unusual wraparound structure, a perfectly flat universe is generally assumed to be infinite, extending in every direction without limit, in the straightforward sense already explored in the discussion of eternal inflation. So which of these three geometries does our actual universe possess? This is not a question cosmologists have simply speculated about. It is a question they have actually gone and measured, using one of the most remarkable pieces of forensic science ever conducted on the fabric of reality itself. The method relies on that same ancient microwave afterglow mentioned earlier, the fossilized light released roughly 380,000 years after the beginning, at the precise moment the young universe cooled enough for light to travel freely for the first time, rather than being constantly scattered by a dense fog of charged particles. This afterglow, called the cosmic microwave background, is remarkably uniform across the entire sky, but not perfectly so. It contains tiny, extraordinarily subtle temperature fluctuations, ripples frozen into the fabric of that ancient light, caused by minuscule variations in the density of matter in the infant universe, the very same variations that would eventually, over billions of years, gravitationally collapse into the first stars, galaxies, and galaxy clusters. These ripples have a characteristic, calculable size, a size determined by the physics of sound waves propagating through the hot, dense plasma of the early universe before it cooled enough to become transparent. Physicists can calculate, with impressive precision, exactly how large these ripples should appear to us today, purely as a function of distance and geometry, but only if space is perfectly flat. If space possesses positive curvature, like the surface of a sphere, then light traveling from those ripples to us would be gently bent inward as it traveled, causing the ripples to appear larger in the sky than a flat space calculation would predict. In the same way a magnifying lens, itself a curved surface, makes an object appear larger than its true size. If space possesses negative curvature, the opposite effect occurs. The ripples would appear smaller than the flat space prediction, their light having been subtly spread apart during its journey. When this measurement was actually carried out, first by a series of balloon-borne and ground-based experiments in the late 1990s and early 2000s, and later refined to extraordinary precision by dedicated satellite missions, the result came back astonishingly close to flat. Not approximately close, in the way a rough estimate might land somewhere in the general vicinity of an answer, but precisely close, with the measured curvature of the universe pinned down to within a fraction of a percent of perfectly flat, across the largest scales current instruments can probe. This is, on its own, one of the more remarkable findings in the entire history of cosmology, and it carries a curious, almost paradoxical implication. A universe that happens to be very close to flat today, this many billions of years into its expansion, must have been almost exactly, precisely flat in its earliest moments, because any deviation from perfect flatness in the early universe, even an extraordinarily tiny one, would have been dramatically amplified by billions of years of subsequent expansion, the same way a barely perceptible wobble in a spinning top becomes a wild, obvious oscillation as the top continues spinning and losing energy. The fact that we observe near-perfect flatness today, despite this amplifying effect, implies the early universe was flat to a degree of precision almost too fine to comfortably imagine. Deviations, if any existed at all, smaller than one part in many, many trillions. This puzzle, known among cosmologists as the flatness problem, was, historically, one of the central pieces of evidence motivating the development of inflationary theory in the first place. A brief, explosive burst of expansion in the earliest fraction of a second, of exactly the kind described earlier, would naturally stretch and smooth out whatever curvature the universe originally possessed, flattening it the same way stretching the surface of a balloon to an enormous size would flatten out any small-scale wrinkles or bumps present on its surface, even if the balloon started out quite irregular. Inflation does not merely help explain why the universe is flat. In many models, it essentially guarantees near-perfect flatness as an almost unavoidable byproduct of the mechanism itself, regardless of whatever curvature preceded it. So where does this leave our question about a closed, finite universe where a traveler could circumnavigate the cosmos and return home? The honest, current scientific answer is this: our universe is either perfectly flat or so close to flat that any residual curvature, positive or negative, would only become measurable, if ever, across distances far, far larger than our 46 billion light-year observable horizon, likely requiring instruments and techniques far beyond anything currently available or even conceivable with present technology. The possibility of a closed, spherical geometry has not been ruled out. It remains an open, actively studied question. But the balance of current evidence leans toward a universe that is flat, or very nearly so, which pushes our exploration, almost inevitably, back toward the strange, boundary-dissolving implications of infinite space, and the causal, rather than spatial, frontiers explored in the discussion of cosmic inflation. It is worth adding one further layer of nuance to the discussion of a closed, spherical universe, because the story of how physicists came to even consider this possibility carries its own fascinating history, one intertwined with some of the strangest and most productive intellectual struggles in the early development of general relativity itself. When Einstein first applied his newly completed equations of general relativity to the universe as a whole, in the years following their publication, he encountered an uncomfortable problem. His equations, applied to a universe filled more or less uniformly with matter, refused to describe a static, unchanging cosmos, the very picture Einstein, along with essentially every other physicist and astronomer of his era, simply assumed to be obviously true, since the night sky, observed over any human timescale, appears eternally fixed and unchanging. Gravity, being purely attractive, should cause a static distribution of matter to collapse inward under its own weight, precisely the way releasing a ball in midair causes it to fall rather than remain suspended. Einstein's equations, taken at face value, predicted exactly this kind of collapse, or alternatively, expansion, anything but the calm, static, eternal universe everyone of that era took for granted. Rather than accepting this prediction, Einstein made a modification to his own equations, introducing an additional term, a kind of built-in repulsive force operating uniformly throughout space, precisely calibrated to counteract the attractive pull of gravity and hold his model universe in a stable, unchanging balance. He called this term the cosmological constant, and he further proposed, in this same early work, that the overall geometry of this static universe should be positively curved, closed, finite, spherical, in the sense discussed at length earlier, reasoning that a finite, bounded distribution of matter arranged around a closed spherical geometry provided the most mathematically elegant and physically sensible way to avoid the awkward question of what might lie at the literal edge of an infinite, unbounded distribution of matter suspended in otherwise empty space. Einstein later famously described the introduction of this cosmological constant as one of the great blunders of his career, a description that has become so widely repeated in popular science writing that it is worth adding some careful context, because the actual history is somewhat more layered and more interesting than the simple great blunder narrative suggests. When Hubble's observations in the following decade revealed that the universe was not static at all, but was actually expanding, Einstein's original motivation for introducing the cosmological constant, preserving a static universe, evaporated entirely, and he reportedly regretted having introduced a seemingly unnecessary complication into his otherwise elegant equations purely to prop up an assumption that turned out to be simply wrong. And yet, remarkably, in a twist that even Einstein himself did not live to see, the cosmological constant would return to the very center of physics decades later, following the same 1998 supernova observations discussed earlier that revealed the accelerating expansion of the universe. That acceleration requires exactly the kind of built-in repulsive effect Einstein originally proposed, not to hold a static universe motionless, as he had originally intended, but to actively push an already expanding universe to expand ever faster. Modern cosmology has reintroduced the cosmological constant, under the more contemporary label of dark energy, as one of the central components of the standard cosmological model, now understood to constitute roughly 2/3 of the total energy content of the observable universe, dwarfing the contribution of ordinary matter and even the mysterious, gravitationally influential but otherwise undetected substance known as dark matter. This history matters for our discussion because it illustrates something valuable about the closed, spherical universe possibility explored earlier. It was not a fringe or eccentric idea invented purely for the sake of philosophical curiosity about edges and boundaries. It emerged directly from some of the most careful, foundational work in the entire history of theoretical physics, considered seriously by Einstein himself as among the most natural, elegant solutions available to his own equations, and it remains, even after the abandonment of Einstein's original static universe model, a live and carefully studied possibility within contemporary cosmology, tested against increasingly precise measurements of cosmic curvature with each passing decade, even as those same measurements continue, so far, to favor a universe remarkably close to flat. There is a further wrinkle worth adding here, one that brings this discussion of curvature back into direct contact with the more exotic multiverse possibilities explored later in this piece. Some contemporary theoretical work, drawing on the same eternal inflation framework discussed at length earlier, suggests that individual bubble universes forming within an eternally inflating field might not necessarily be flat or infinite at all, but could, depending on the specific details of how a given bubble nucleates and evolves, actually possess a slight negative curvature, an open, rather than closed, geometry, distinct from both the flat universe discussed in connection with ordinary inflation and the closed, spherical universe Einstein originally favored. Under this particular theoretical picture, our observable universe's remarkably close approach to flatness would not necessarily indicate that the universe as a whole is perfectly, exactly flat everywhere, but might instead reflect the fact that our particular bubble is so enormously large, relative to our comparatively tiny observable portion of it, that even a bubble with genuine, non-zero negative curvature could appear, from deep within it, indistinguishable from perfect flatness across any distance current instruments can measure, in the same way a small patch of the Earth's genuinely curved surface appears, to someone standing on it without specialized surveying equipment, essentially indistinguishable from a perfectly flat plane. This particular hybrid possibility, an open, negatively curved bubble universe nested within a broader eternally inflating multiverse, has attracted serious theoretical attention precisely because it offers a way of potentially reconciling several of the major frameworks discussed throughout this piece, rather than treating them as four entirely separate, mutually exclusive possibilities that could not, in principle, coexist within some larger, more complete cosmological picture. It remains, like nearly everything at this particular frontier of theoretical physics, difficult to test directly, and it has not displaced the simpler, flat, single universe models that continue to provide the best overall fit to the majority of current observational data. But it stands as a useful reminder that the four possibilities explored across this piece, the light horizon, the closed sphere, the infinite flat expanse with its causal boundary, and the multiverse landscape, need not necessarily be understood as four entirely separate, competing, mutually exclusive answers to a single question. They may, in some future, more complete theoretical framework not yet fully developed, turn out to be different facets of a single, more elaborate underlying picture, each one correctly capturing some genuine aspect of a reality too large and too strange to be fully contained within any single, simple analogy, a sphere, a flat expanse, a boiling pot, a mirror maze, no matter how carefully or how honestly that analogy is constructed. There is, however, another possibility on the table, one that current measurements actually favor as the simpler and statistically more probable option, and it demands that we abandon the sphere entirely and consider something almost impossible to hold in a single thought, a universe that is not curved at all, but perfectly, geometrically flat, and, in that flatness, quite possibly infinite. It is worth letting that word do its actual work, rather than sliding past it the way it so often does in casual conversation. Not extremely large. Not larger than current instruments can measure. Infinite. A universe with no boundary in space because space itself never runs out. A canvas with no edges to run off of, extending in every direction without limit, filled, presumably, with structure and matter arranged in roughly the same statistical patterns we observe here, over and over, without ever concluding. If this is the true shape of the cosmos, then the question of a spatial edge does not merely become difficult to answer, it dissolves entirely, because there is nothing there to find. It is impossible to reach the edge of something that has no edge to reach. In precisely the same way, it is impossible to count to the last number. Not because counting is too hard, or because time would run out, though it certainly would, but because the entire premise of a last number contradicts the very structure of what numbers are. An infinite universe treats the concept of an edge the same way infinite mathematics treats the concept of a largest integer, as a category error, a question built from words that do not actually combine into a coherent thing to search for. And yet, and this is where the story becomes genuinely strange, and where the modern theory of cosmic inflation enters, even an infinite universe can contain something that behaves, for all practical purposes, like a frontier. Not a frontier in space. A frontier in causality itself. Understanding this requires revisiting something mentioned earlier, almost in passing, but which deserves far more attention. The fact that space itself is expanding, and that this expansion is not bound by the speed of light in the way the movement of objects through space is bound. This distinction trips up nearly everyone the first time they encounter it, so it is worth being extremely precise. Einstein's speed limit, nothing travels faster than light, applies to things moving through space. A spaceship, a beam of light, a radio signal, all of these are constrained. But the expansion of space itself is a different phenomenon entirely. It is not a thing moving through space, it is the stretching of the space through which things move. And there is no law of physics that limits how fast that stretching can occur between two sufficiently distant points. Picture two ants standing on the surface of a balloon, each holding one end of a piece of string stretched between them. As the balloon inflates, the ants do not walk anywhere. Neither one takes a single step. And yet the distance between them increases, because the rubber surface itself, the space they inhabit, is expanding beneath their feet. Push this analogy far enough, imagine a balloon large enough and points on its surface distant enough, and the rate at which those two ants separate, purely from inflation, could in principle exceed any speed limit governing their own individual movement. The ants aren't moving fast. The balloon is stretching fast. This is, almost exactly, what is happening throughout our universe at every moment. Galaxies sufficiently far from us are not racing away through space at incredible velocities in the way a rocket might. Space itself, in the vast gulfs between us and them, is expanding, carrying those galaxies farther away as a passive consequence of the geometry stretching beneath them. And because there is no limit on how fast that stretching can occur across sufficiently large distances, there exist regions of the universe, right now, at this very moment, that are receding from us faster than light could ever cross the gap to reach us. Here is the consequence that transforms an infinite universe from a purely mathematical abstraction into something with real, tangible structure. Once a region begins receding faster than light, no signal, no information, no photon of any kind emitted from that region will ever be able to catch up to us. Not eventually. Not given enough time. Never. The gap between us is not merely large. It is actively growing faster than anything traveling through it could possibly close. That region has been permanently, physically severed from any causal connection with our own patch of the cosmos. This creates what cosmologists sometimes call a causal boundary, or an event horizon in the cosmological sense, not the edge of space, since space in this scenario has no edge, but the edge of connection. The edge of could ever, even in principle, affect us or be affected by us. Beyond this boundary lies a portion of the universe that, for all functional purposes, might as well exist in an entirely separate reality, even though it is, technically, part of the same continuous, unbroken, infinite fabric of space. And the theory of cosmic inflation adds one more layer to this picture, arguably the strangest layer of all. In the earliest fraction of a second after the beginning, our universe is thought to have undergone an almost unimaginably rapid burst of expansion, a moment when space itself stretched by a factor so enormous that a region smaller than a single atom ballooned, in a fraction of a second, to a size larger than the observable universe is today. This process, inflation, is believed to be what smoothed out the early universe into the remarkably uniform, remarkably flat structure we observe in every direction we look. But here is the detail most casual explanations skip entirely, and it may be the single most consequential idea in this entire exploration. Many of the leading models of inflation suggest that this explosive expansion, once triggered, does not naturally stop everywhere at once. In our region, inflation ended, matter condensed, stars ignited, the long, patient work of chemistry and gravity began building galaxies, planets, and eventually creatures capable of asking where the edge of it all might be. But in other regions, according to these models, inflation simply never stopped. It continues, endlessly, an eternal, boiling, energy-saturated expansion that never settles down into the calm, structured cosmos we happen to inhabit. This is sometimes called eternal inflation, and under this framework, our entire observable universe, every galaxy, every star, all 46 billion light-years of radius in every direction, represents nothing more than a single localized region where the inflationary process happened to end, a single cooled, settled pocket within an incomprehensibly larger, still boiling sea of raw expansion. The edge, in this model, is not a wall and not even, strictly speaking, a place in the traditional sense. It is a phase boundary, the transition zone where the frantic, undifferentiated energy of eternal inflation gives way to the cooled, structured, matter-filled universe we call home. Our entire cosmos, in this picture, resembles nothing so much as a single bubble of calm water momentarily forming within a pot still at a full, roiling boil, an island of order surrounded, at unreachable distances, by a chaos still actively being born. It is a genuinely dizzying picture, and it is important to be honest about its status. Eternal inflation remains a theoretical framework, one that follows logically from the physics of inflation as we currently understand it, but one that has not been, and, by its very nature, quite possibly cannot ever be, directly confirmed through observation, since anything happening beyond our causal horizon is, definitionally, beyond our ability to observe. It sits at the frontier of testable science, a mathematically consistent and physically motivated extrapolation, but an extrapolation nonetheless. Still, even as an open question, it forces a profound reframing. If eternal inflation is correct, then the edge of the universe is not spatial at all. It is temporal and thermodynamic, a boundary not between here and there, but between settled and still becoming. Our 46 billion light-year sphere of calm, star-filled space would be, on this cosmic scale, something closer to a single snowflake that has managed to crystallize within a storm that, everywhere else, is still raging. There is a second, quieter sense in which the universe possesses an edge, not a boundary in space, and not, strictly speaking, a boundary in the causal sense discussed a moment ago, but a boundary in time, arrived at not through geometry but through thermodynamics. It deserves its own careful treatment, because it reframes the entire question of the end of everything in a way that has nothing to do with distance at all. Every physical process in the universe, without exception, obeys a principle so fundamental that physicists sometimes half-jokingly call it the only law of physics that has never once been observed to be violated, under any circumstance, at any scale, the second law of thermodynamics. Stated simply, it says that in any closed system, disorder, a quantity physicists call entropy, never decreases over time. It can stay the same, in perfectly idealized circumstances that never actually occur in the real world, but overwhelmingly, relentlessly, it tends to increase. This law plays out constantly in ordinary experience, even when no one is thinking of it in these terms. A cup of hot coffee left on a table does not spontaneously grow hotter, drawing warmth out of the cooler air around it and becoming concentrated back into the cup. It cools, its heat dispersing outward into the room, disorder increasing as concentrated thermal energy spreads into a more diffuse, more evenly distributed, less useful state. An ice cube left in a warm room does not spontaneously reform from a puddle. A shattered glass does not spontaneously reassemble itself from scattered fragments back into a single intact vessel. In every one of these examples, energy is not being destroyed. The total amount remains exactly the same, in strict accordance with the equally fundamental law of energy conservation. What changes is the quality, the usefulness, the organization of that energy. It moves, inexorably, from concentrated, structured, useful configurations toward diffuse, disordered, less useful ones. Now extend this principle across the largest possible scale, the entire universe, treated as a single, isolated thermodynamic system with nothing outside it to exchange energy with. Every star currently burning in the night sky is, in thermodynamic terms, a temporary, localized pocket of extraordinary order, a dense concentration of hydrogen and helium, fusing under gravitational pressure, releasing energy in a structured, useful form that radiates outward, providing the light and warmth that made life on Earth possible in the first place. But every star is also, simultaneously, a countdown clock. Every fusion reaction inside every star's core is converting a small amount of highly ordered nuclear potential energy into a much larger amount of disordered thermal radiation, spreading outward into the emptiness of space, never to be reconcentrated. Stars do not run on an inexhaustible supply of fuel. They run on a finite reservoir of hydrogen, slowly, irreversibly converting order into disorder, structure into heat, over spans of millions or billions of years, until that reservoir runs dry. Zoom out from any single star to the universe as a whole, and the same relentless arithmetic applies at every scale simultaneously. Galaxies will, over spans of time almost too large for ordinary numbers to convey meaning, exhaust their supply of star-forming gas. The stars that do form will, one by one, burn through their nuclear fuel, some collapsing into dense white dwarfs that will spend inconceivable eons slowly radiating away their residual heat into the cold of space, others detonating as supernovae and scattering their material outward, enriching the surrounding gas with heavier elements before that gas, too, is eventually consumed. Black holes, the most extreme concentrations of gravity and matter the universe produces, are not, contrary to a common misconception, eternal and unchanging either. Stephen Hawking's theoretical work in the 1970s demonstrated that even black holes slowly radiate away their mass over unfathomably long timescales, through a subtle quantum process now called Hawking radiation, eventually evaporating entirely, converting even the densest structures the universe has ever produced into a final, diffuse mist of low-energy radiation. Run this process forward far enough, not billions of years, not trillions, but a span of time so vast that scientific notation itself becomes almost the only sane way to express it, and cosmologists arrive at a projected future state sometimes called the heat death of the universe, or, in more technical language, maximum entropy or thermodynamic equilibrium. In this state, every star has burned out. Every black hole has evaporated. Every concentration of usable energy has, eventually, dispersed into an almost perfectly uniform, extraordinarily cold, extraordinarily diffuse bath of low-energy radiation, spread with near-perfect evenness across a universe that, by this point, driven by the same accelerating expansion discussed earlier, has grown to a size that makes even today's 46 billion light-year observable radius look, by comparison, like a single grain of sand. In this state, nothing meaningfully changes anymore. There is no more usable energy gradient to drive any physical process, no temperature differences to power a star, no chemical gradients to power a reaction, no gravitational structure left uncollapsed and undissipated. Time, in the sense of things happening, effectively stops mattering, even though time itself, as a dimension, presumably continues indefinitely. It is a state of profound, absolute stillness, not the violent stillness of a frozen moment, but the exhausted stillness of a system that has spent every available resource it will ever have. Why does this belong in a discussion about the edge of the universe? Because it represents another entirely legitimate answer to a question closely related to our original one. Not where does the universe end, but when, in some meaningful sense, does the universe's story end? It is a boundary drawn not in space, and not exactly in the causal sense discussed with eternal inflation, but along the axis of usable order, of structure, of the capacity for anything interesting to ever happen again. Beyond this thermodynamic edge, in a strange sense, lies not a place but an endless, changeless duration, a universe that has not ceased to exist, but has exhausted every capacity it ever had to produce anything resembling an event. There is something worth sitting with here, a kind of quiet, sobering symmetry with the earlier discussion of the causal horizon created by cosmic expansion. Both concepts describe, in their own way, an ultimate isolation. The causal horizon isolates us in space, cutting off communication with regions receding faster than light. The heat death isolates the universe in time, exhausting the very engine, usable energy gradients, that makes any communication, any structure, any event of any kind possible in the first place. Together, they paint a picture of a cosmos that is, in the most literal sense achievable within known physics, running down, not toward some external edge waiting to be reached, but toward an internal exhaustion, a slow, inexorable spending of a finite inheritance of order that was, in some sense, set at the very beginning, in that first almost incomprehensibly hot, dense, low-entropy state from which everything else in this exploration has taken its starting point. It is worth noting, too, that this projected fate is not entirely without its own open questions and alternative possibilities, much like every other topic addressed so far. Some theoretical work suggests that on truly cosmological timescales, quantum fluctuations within an eternally expanding, maximally disordered universe could, purely by extraordinarily improbable chance, spontaneously generate small, localized, temporary pockets of low entropy, brief flickers of order arising randomly from the underlying quantum vacuum, the way an astronomically unlikely, but not technically impossible, string of coin flips could eventually produce a long unbroken run of heads, purely through chance, given enough attempts and enough time. Whether such fluctuations could ever produce anything resembling a new universe, a new Big Bang, a fresh restart of the entire process, remains deeply speculative and is debated within a fairly narrow corner of theoretical physics, viewed by some researchers as a genuine possibility worth taking seriously and by others as a mathematical curiosity unlikely to reflect anything physically meaningful. But even this speculative possibility only reinforces the central point. Whatever ultimately happens at the furthest possible extension of time, it is not, and was never going to be, a wall. It was always going to be a gradual, thermodynamic dissolution, an edge measured not in light years, but in the slow, patient arithmetic of disorder increasing, one star, one galaxy, one evaporating black hole at a time, until the very last usable difference the universe will ever produce has finally, quietly, been spent. There remains one final possibility, and it is, by a wide margin, the strangest of the four, a proposal so far removed from ordinary experience that even physicists who work with it daily often reach for science fiction language to describe it, not because the physics is fictional, but because human language was never built with these particular concepts in mind. What if our entire universe, every galaxy, every star, all 46 billion light-years of observable radius, the entirety of the causally connected structure discussed a moment ago, is not the whole of existence at all, but a single bubble, a single localized event, drifting within some far vaster structure that contains countless other such bubbles, each one operating under its own separate, self-contained set of physical laws? This is the proposal, broadly, of what has come to be called the multiverse, though it is worth noting immediately that this single word is used to describe several genuinely distinct theoretical frameworks, arising from different branches of physics, which sometimes agree with one another and sometimes do not. The version most relevant to our question about a physical edge comes from a combination of string theory and the inflationary cosmology discussed a moment ago, and it offers an image both beautiful and deeply unsettling. Picture a pot of water brought to a rolling boil. Looked at closely, the surface is not uniform. It is alive with bubbles, some rising and vanishing almost instantly, others swelling large before bursting, the whole surface a chaotic, constantly shifting field of localized pockets forming and collapsing within the larger churning mass of water. Now imagine, instead of a pot of water, an infinite, eternally inflating field of raw quantum energy, the very structure introduced in the previous section, and imagine that occasionally, within this endless boiling, a region undergoes a kind of phase transition, cooling and settling into a stable pocket with its own internal physical laws, its own set of fundamental constants, its own version of matter and energy and structure. Each of these pockets is what physicists, borrowing the string theory term, sometimes call a bubble universe, bounded by an almost impossibly thin membrane, in the language of string theory, a brane, short for membrane, extended across whatever dimensions define its particular pocket of existence. Our own universe, under this framework, is one such bubble. And the edge of our universe, in this picture, is the surface of that bubble itself, not a wall in the ordinary sense, not a barrier made of any substance we could recognize, but a boundary between one set of physical rules and an entirely different, potentially unrecognizable set of physical rules operating just beyond it. This is worth dwelling on, because it is easy to let the word boundary smuggle in assumptions that do not actually belong here. When we imagine crossing from inside a house to outside a house, we imagine a doorway, a transition between two spaces that still obey the same laws of physics, the same gravity, the same chemistry, simply arranged differently. Crossing the boundary of a bubble universe, in this model, is nothing like that. On the other side of that membrane, the fundamental constants of nature, the strength of gravity, the mass of an electron, the number of spatial dimensions a physical object can even occupy, could be entirely different. Some theoretical frameworks derived from string theory suggest there may be an almost unfathomable number of possible stable configurations for these constants, sometimes described using a number so large it borrows more from combinatorics than from any everyday intuition about many, a landscape of possible universes so vast that our own particular combination of physical laws, the laws that allow atoms to be stable, chemistry to function, and eventually life to exist, might be just one specific, perhaps even statistically unlikely, outcome among a staggering number of alternatives. Consider what this would actually mean for anything attempting to cross such a boundary. It would not experience anything resembling falling off an edge into empty space. There would be no sensation of tumbling into a void, because falling itself requires gravity to behave in a familiar way, and there is no guarantee gravity behaves at all beyond that membrane. The atoms composing any object attempting the crossing are held together by a precise, delicate balance of fundamental forces, the same forces, incidentally, that keep solid ground solid and keep breathable air from simply drifting apart into its constituent particles. Those forces exist in their current, stable configuration specifically because the physical constants inside our particular bubble happen to permit them. Strip away that specific configuration, replace it with whatever arbitrary set of constants might govern the region beyond the membrane, and there is no reason to expect atoms, in any form we would recognize, to continue existing as coherent structures at all. In other words, crossing this particular kind of edge would not be a journey into somewhere else. It would be, functionally, an instantaneous unmaking, not death in any biological sense, not destruction in any sense involving force or impact, but a far stranger dissolution, the simple and total cessation of the specific physical arrangement that had, until that exact moment, constituted a coherent object at all. The rules that had been quietly, invisibly holding every proton and electron in its proper place would simply no longer apply, in the same abrupt, absolute way that the rules of chess no longer apply the instant a player steps away from the board. It is a genuinely difficult image to hold in the mind, precisely because it resists every intuition built from a lifetime spent inside a single, stable set of physical laws. We have never, not once, in the entire history of our species, encountered a region where gravity simply behaves differently, where atoms are held together by some other configuration of forces, where the number of spatial dimensions available for motion might not even be 3. Every explorer in human history who has ever pushed past a previous boundary, an ocean, a mountain range, a continent, has always, without exception, found more of the same universe on the other side, the same laws of chemistry, the same gravity, the same fundamental physics, merely arranged into new and unfamiliar configurations of matter. The multiverse hypothesis proposes something categorically different, an edge beyond which even the rulebook itself changes. It must be stated, with full scientific honesty, that this remains among the most speculative ideas in contemporary theoretical physics, deeply motivated by the internal mathematics of string theory and by certain models of eternal inflation, taken seriously by a significant portion of the theoretical physics community, but currently lacking any direct observational test, and possibly, by its very nature, permanently beyond the reach of direct confirmation, since any genuine other universe would, almost by definition, exist entirely outside our causal horizon. Some physicists find the idea compelling precisely because it emerges naturally from equations developed for entirely different purposes, without being deliberately engineered to produce a multiverse. Others regard it with genuine skepticism, arguing that a theory which cannot, even in principle, be tested occupies an uncomfortable position at the very boundary of what should be called science at all. This tension is real, ongoing, and worth acknowledging honestly rather than glossing over. But whether or not the specific mechanics of bubble universes and brands turn out to describe physical reality, the concept itself accomplishes something valuable. It completes the spectrum of possibilities for what an edge to the universe could even mean. It is the final, most radical rung on a ladder that began with the comparatively mundane limitation of light's travel time, climbed through the elegant geometric closure of a curved, finite yet unbounded cosmos, ascended further into the causal severance created by an ever-accelerating expansion within a possibly infinite space, and arrives, finally, at a boundary between entire systems of physical law themselves, a genuine edge not of space, not of time, but of reality's own operating rules. To understand why serious physicists, rather than science fiction writers, began taking the idea of a multiverse seriously in the first place, it helps to trace the actual scientific path that led there, because it did not begin as an attempt to answer the question, what lies beyond our universe? It began, almost accidentally, as an attempt to solve much more mundane, technical problems within particle physics, and only later did physicists realize the framework they had built carried this staggering implication as an almost unavoidable side effect. String theory, which emerged in various forms across the latter half of the 20th century, was originally developed as an attempt to unify two great pillars of modern physics that had, for decades, stubbornly refused to fit together: general relativity, which describes gravity magnificently at large scales, and quantum mechanics, which describes the behavior of particles magnificently at small scales, but which produces nonsensical, infinite results whenever physicists try to apply its methods directly to gravity itself. The core proposal of string theory was elegant, at least in its initial framing. Rather than treating the fundamental building blocks of reality as point-like particles, treat them instead as extraordinarily tiny, vibrating one-dimensional strings, with different vibration patterns corresponding to different particles, the way different notes emerge from different vibration patterns on a guitar string. This proposal, in order to be mathematically consistent, required something that struck most people, on first hearing it, as bizarre: extra spatial dimensions beyond the 3 we experience directly. Not one extra dimension, but, depending on the specific version of the theory, 6 or 7 additional spatial dimensions, curled up, compactified, folded into shapes so small that they remain utterly undetectable at any scale humans can currently probe, in the same way a garden hose, viewed from a great distance, appears to be a simple one-dimensional line, even though anyone standing close enough could see that its surface actually wraps around a second, circular dimension. Here is where the story takes its unexpected turn toward the multiverse. The precise geometric shape into which these extra dimensions curl up is not fixed by the theory itself. String theory does not predict one single, unique shape. It permits an enormous number of possible shapes, and each distinct shape, once worked through the resulting mathematics, produces a universe with a different set of fundamental physical constants, different particle masses, different force strengths, potentially even a different effective number of large, uncurled spatial dimensions. The precise number of possible shapes is a subject of ongoing calculation and some genuine scientific disagreement, but estimates within the theoretical physics literature have proposed figures so large that they are often expressed using scientific notation involving hundreds of zeros, a number sometimes referred to, somewhat informally, as the string theory landscape. This landscape, in other words, is not a single theory predicting a single universe. It is a vast mathematical space of possible universes, each corresponding to a different way the extra dimensions could curl up, each with its own distinct physics. And this is precisely where eternal inflation, discussed earlier, connects to string theory in a way that produces the multiverse hypothesis in its most commonly discussed modern form. If eternal inflation is correct, and different regions of the eternally inflating field can settle into different stable configurations as they cool, the way water can freeze into ice in one location while remaining liquid nearby, depending on local conditions, then it becomes natural, even difficult to avoid, to imagine that different bubble universes forming throughout an eternally inflating field might settle into different points within the string theory landscape, each one crystallizing into its own distinct combination of physical laws. Our universe, on this view, would be one specific settlement within this landscape, one particular configuration of curled-up extra dimensions, producing our particular values for the mass of an electron, the strength of the electromagnetic force, the number of large spatial dimensions we experience as 3. Elsewhere, in other bubbles, other settlements would have occurred, each producing a genuinely different universe, potentially unrecognizable by our own physical standards. This is where an idea called anthropic reasoning enters the discussion, and it deserves careful, honest treatment, because it is frequently misunderstood, misrepresented, or dismissed too quickly by critics and enthusiasts alike. Anthropic reasoning does not claim that the universe was designed for observers to exist. It makes a much more modest, almost tautological point. Whatever universe we happen to find ourselves observing must, necessarily, be one capable of producing observers, because if it were not, there would be no one present within it to do any observing at all. Among an enormous landscape of possible universes with wildly different physical constants, the overwhelming majority might be sterile, incapable of forming stable atoms, incapable of forming stars, incapable of producing the long chains of chemistry that eventually give rise to anything resembling life. Only a small subset of the landscape, the argument goes, would happen to possess the specific, delicately balanced combination of constants that allows for complexity, chemistry, and eventually consciousness to emerge. And it should therefore come as no particular surprise that we, as observers who exist and are capable of asking the question, find ourselves within one of those rare, life-permitting bubbles, rather than one of the vastly more numerous sterile ones. In the same way, it should be no surprise that a fish, capable of pondering its own existence, finds itself living in water rather than on dry land, even though dry land constitutes the overwhelming majority of the Earth's surface. This reasoning has been invoked, in particular, to address a long-standing puzzle in physics sometimes called the fine-tuning problem, the observation that several of the fundamental constants governing our universe appear to sit within an extraordinarily narrow range of values that permit complex structure to exist at all. The strength of the force binding atomic nuclei together, for instance, appears finely balanced in such a way that if it were even a few percent stronger or weaker, the specific nuclear fusion processes that produce carbon inside stars, carbon being, as far as we currently understand biochemistry, essential to any conceivable form of life, would not occur in anything close to the necessary abundance. Some physicists find this apparent fine-tuning deeply significant, a mystery-demanding explanation. Others regard it as, at least in part, a natural consequence of anthropic selection within a sufficiently large and varied multiverse. Given enough bubbles, enough variety, enough attempts, it becomes almost statistically inevitable that at least some small fraction would happen to land in the narrow range permitting complexity. And, again, it is only within those rare fractions that anyone would ever exist in the interest of intellectual honesty to present the serious scientific pushback against this entire framework as clearly as the framework itself, because this is one of the more genuinely contested areas within contemporary theoretical physics, and pretending otherwise would do a disservice to the actual state of the field. The central and most frequently voiced objection concerns falsifiability, the principle, central to the modern scientific method since the work of the philosopher Karl Popper in the mid-20th century, that a genuinely scientific theory must, at least in principle, be capable of making predictions that could be shown to be wrong through observation or experiment. Critics of the multiverse hypothesis, including a number of highly respected physicists, argue that because other bubble universes lie, by their very definition, beyond any possible causal contact with our own, no experiment, no observation, no measurement of any conceivable kind could ever directly confirm or refute their existence. A theory that permanently escapes any possible test, these critics argue, however elegant its underlying mathematics, risks drifting away from empirical science and towards something closer to philosophical speculation dressed in the vocabulary of physics. Proponents of the framework generally respond to this criticism in one of two ways, and both deserve to be heard on their own terms. The first response argues that while individual other universes cannot be directly observed, the overall theoretical framework that predicts them, the combination of inflationary cosmology and string theory, was developed for independent reasons, to solve independent problems, such as the flatness problem discussed earlier or the technical unification of gravity and quantum mechanics, and happens to produce the multiverse as an unavoidable mathematical consequence, rather than being deliberately constructed to produce it as a desired conclusion. On this view, the framework as a whole remains testable and has, in various specific predictions unrelated to the multiverse itself, already passed a number of observational checks. The multiverse is simply an implication that comes bundled with an otherwise well-motivated and independently testable theoretical structure, in the same way that general relativity, developed to explain gravity, also predicts black holes as an unavoidable mathematical consequence, even though no one set out specifically trying to predict black holes when developing the theory. The second response is more philosophically ambitious and, correspondingly, more contested. Some physicists argue that indirect statistical evidence, of the kind anthropic reasoning provides regarding the apparent fine-tuning of physical constants, constitutes a legitimate, if unconventional, form of scientific support, even in the absence of any possible direct observation of other universes. Critics remain skeptical of this move, arguing that it risks lowering the bar for what counts as scientific confirmation to a degree that could, in principle, be used to justify almost any sufficiently flexible theoretical framework. This debate remains genuinely, actively unresolved within the physics community, discussed at length in academic papers, conference panels, and popular science books written by physicists on opposing sides of the question. It is presented here not to resolve it, no one currently can, but because an honest exploration of what might lie at the edge of our universe would be incomplete, even dishonest, without acknowledging that the most radical of the proposed answers sits at a genuinely contested boundary of what counts as testable science in the first place. Whether the multiverse is a profound insight into the deep structure of reality, or an untestable mathematical curiosity mistaken for physical truth, remains one of the most fascinating open questions in the entire history of cosmological thought, itself, in a sense, a kind of edge, the edge of what current science can decisively settle, standing right alongside the edge of the universe it was originally invoked to describe. There is one more physical structure worth examining closely before drawing these threads together, because it offers something the other three possibilities largely cannot, an edge we have actually, directly, observationally confirmed exists, sitting right here within our own observable universe, close enough to study, photograph, and test against real data. That structure is the event horizon of a black hole, and understanding it in detail provides perhaps the single most intimate, tangible intuition available for what a cosmological horizon actually is and is not. A black hole forms when an enormous concentration of mass collapses into an extraordinarily small volume, creating a gravitational field so intense that, past a certain distance from its center, the escape velocity required to break free of its pull exceeds the speed of light itself. Since nothing, according to every confirmed law of physics, can travel faster than light, this means that past this critical distance, nothing, no particle, no signal, no photon of light itself, can ever escape once it has crossed that threshold. This threshold has a name, the event horizon. It is worth being extremely precise about what the event horizon actually is, because popular depictions of black holes frequently distort this in ways that create lasting misconceptions. The event horizon is not a physical surface. It is not made of any material substance. There is no wall to strike, no membrane to physically feel resistance against, no marker floating in space announcing its presence to anyone crossing it. It is, instead, a purely geometric boundary, a specific distance from the black hole center at which the curvature of spacetime, caused by the concentrated mass, becomes so extreme that all possible paths, all possible trajectories, no matter which direction an object attempts to travel, inevitably lead inward, toward the center, rather than outward, toward escape. This is worth dwelling on with a careful analogy of its own, because it clarifies something essential about horizons in general, cosmological and otherwise, that will prove directly relevant to the causal horizon discussed earlier in the context of cosmic expansion. Imagine a swimmer caught in a powerful river current, approaching a waterfall. Far upstream, the current is gentle enough that a strong swimmer can still make progress against it, swimming toward the shore, toward safety, away from the coming drop. But there exists a specific point in the river, a precise location, calculable given the river's flow rate and the swimmer's maximum swimming speed, beyond which the current has become faster than the swimmer's best possible upstream effort. Past this point, no matter how hard the swimmer works, no matter how skilled or strong they are, they will be carried over the falls. Their fate is sealed the instant they cross that specific point, even though nothing about the water itself changes abruptly at that location. No visible line in the river, no sudden change in color or texture, nothing a swimmer could see or feel that would announce, in the moment of crossing, that their situation had just become unrecoverable. This is, with remarkable fidelity, the actual physics of an event horizon. A hypothetical astronaut falling toward a sufficiently large black hole would, according to general relativity, feel nothing unusual at the precise moment of crossing the event horizon. No jolt, no resistance, no local sensation marking the transition. Locally, from the astronaut's own frame of reference, space-time at the horizon of a sufficiently massive black hole can be nearly as smooth and unremarkable as the vacuum of empty space anywhere else. And yet, from that point onward, every possible path forward through time leads, inevitably, toward the singularity at the center. Escape has not become merely difficult. It has become, in the most literal sense the mathematics of general relativity can express, impossible, not because of any force pushing the astronaut inward, but because the geometry of spacetime itself has been so severely warped that outward and toward the center are no longer meaningfully distinct directions. In the same way, upstream stops being an achievable direction for the swimmer once the current exceeds their maximum possible speed. Here is the connection to the cosmological horizon that emerges from the accelerating expansion of space, discussed at length earlier, and it is a connection professional cosmologists take extremely seriously, not merely as a loose poetic parallel but as a genuine mathematical similarity in the underlying physics. In both cases, an observer approaching or residing near the horizon experiences nothing locally unusual. In both cases, the horizon is defined not by any physical marker but by a relationship between two competing speeds, the speed of light attempting to cross a given distance against the speed at which that distance is being stretched or generated by some other physical process, whether gravitational collapse in the case of a black hole or cosmic expansion in the case of the universe as a whole. And in both cases, crossing the horizon, falling into a black hole, or having a region of space recede beyond the cosmological horizon, represents a permanent, irreversible severing of causal contact. A one-way transition from communication is possible, at least in principle, to communication has become physically, permanently impossible, regardless of how much time is allowed to pass. This parallel runs deep enough that theoretical physicists studying black holes and theoretical physicists studying cosmology frequently borrow techniques, equations, and even entire theoretical frameworks from one another's specialties. The mathematics describing the radiation black holes are the rise to emit as they slowly evaporate. The Hawking radiation mentioned earlier in the discussion of the universe's eventual heat death bears a close mathematical resemblance to certain calculations describing radiation associated with cosmological horizons in an accelerating, expanding universe. Some of the deepest and most actively pursued research questions in contemporary theoretical physics revolve around trying to understand precisely why these two seemingly very different physical situations, the crushing gravitational collapse at the heart of a dying star and the vast, gentle stretching of empty space between galaxies, produce such structurally similar mathematical descriptions of their respective horizons. There is a further, genuinely profound puzzle associated with black hole horizons that deserves mention here, both because it represents one of the most actively debated open problems in contemporary theoretical physics, and because it offers a striking parallel to a question raised earlier regarding the multiverse, the question of what happens, physically, to information that crosses an edge beyond which our ordinary physics no longer straightforwardly applies. When any object falls into a black hole, a star, a spacecraft, a stray hydrogen atom, conventional intuition, along with the foundational principle of quantum mechanics called information conservation, suggests that whatever specific, detailed physical information described that object should not simply vanish from existence, even though the object itself becomes trapped beyond the event horizon, inaccessible to any outside observer. Quantum mechanics, in its standard formulation, treats the loss of information as fundamentally forbidden. The universe, according to this principle, is meant to be a kind of perfect, reversible bookkeeper, in which the complete physical state of anything, in principle, could always be reconstructed from sufficiently complete information about everything it interacted with, even if that reconstruction were, in any practical sense, impossibly difficult. But Hawking's own theoretical work on black hole evaporation seemed, for a period of decades, to suggest a genuine contradiction with this principle. If a black hole slowly evaporates by emitting Hawking radiation, and that radiation appears, according to the relevant calculations, to be almost perfectly random and featureless, carrying no discernible trace of the specific details of whatever originally fell into the black hole, then it would seem that once the black hole has fully evaporated, the specific information describing everything that ever fell into it has been permanently, irrecoverably destroyed, a direct violation of the principle of information conservation that sits at the very foundation of quantum theory. This apparent contradiction became known as the black hole information paradox, and it occupied, and to a significant degree continues to occupy, some of the most talented theoretical physicists working today, including Hawking himself in the later decades of his career, during which his own thinking on the resolution of this paradox shifted and evolved considerably. Recent decades of theoretical work, drawing on sophisticated techniques from an area of physics called holography, have produced results that many, though not all, physicists in the field now believe demonstrate that information is not, in fact, destroyed by black hole evaporation, and that a sufficiently careful accounting of the quantum mechanical correlations within Hawking radiation can, in principle, recover the complete information describing everything that ever fell in, though the precise mechanism by which this happens, and how it should be properly understood physically rather than merely calculated mathematically, remains an active and genuinely difficult area of ongoing research, without full consensus achieved even now. Why does this matter for our exploration of the edge of the universe? Because it demonstrates, in a case we can study with much greater rigor and confidence than the more speculative cosmological scenarios discussed earlier, something valuable about how physics actually treats the concept of an edge. An edge, in the careful, technical sense used throughout modern physics, is rarely a simple, final stopping point where the story of physical law simply concludes. It is, far more often, a region of extreme complexity, extreme subtlety, where our ordinary intuitions break down and where the deepest, most difficult questions about the fundamental nature of information, causality, and reality itself come most sharply into focus. The event horizon of a black hole did not turn out to be a simple point of no return, full stop, end of story. It turned out to be one of the richest, most productive puzzles in all of contemporary theoretical physics, one whose resolution required decades of sustained work and whose full implications are still being worked out today. There is every reason to expect that the true edge of the universe, whichever of the possibilities explored throughout this piece turns out to correspond most closely to reality, will prove to be, in exactly the same way, not an ending but a beginning, not the conclusion of the story of physical law, but the opening of an entirely new, currently unimaginable chapter of it, waiting for a future generation of physicists equipped with tools, mathematics, and perhaps entirely new conceptual frameworks that do not yet exist, to finally, properly begin exploring. It is worth stepping back from the frontiers of theoretical physics for a moment to appreciate something easily taken for granted throughout this entire exploration: the sheer, almost unbelievable achievement represented by our ability to measure any of these distances at all. Numbers like 46 billion light-years, or 13.8 billion years, are recited so casually in popular science writing that it is easy to forget just how extraordinary an accomplishment it is that human beings, standing on the surface of a single small planet, orbiting an unremarkable star, in an unremarkable arm of an unremarkable galaxy, have managed to measure the scale of the entire observable cosmos with a precision rivaling that of far more mundane, earthbound engineering. Measurements. The story of how we came to know the size of the universe is, in many ways, as remarkable as the size itself, and it did not begin with space telescopes or particle accelerators. It began, more than 2,000 years ago, with a scholar in ancient Egypt and a simple, elegant observation about shadows. Eratosthenes, working in the city of Alexandria around the 3rd century before the Common Era, had heard reports that at a certain city to the south, called Syene, at precisely noon on the summer solstice, sunlight struck the bottom of a deep well directly, casting no shadow whatsoever, indicating the sun was positioned directly overhead at that exact moment. On that same day, at that same hour, in Alexandria, Eratosthenes measured the shadow cast by a vertical rod and found it was not zero. The sun was not directly overhead in Alexandria the way it was in Syene. Using the length of that shadow, and some careful geometry involving the angles formed by the sun's rays, Eratosthenes calculated the angular difference between the two cities, and combined this with an estimate of the distance between them, obtained from the travel time of camel caravans along established trade routes. The result of this remarkably simple experiment, a rod, a shadow, some careful geometry, and a rough estimate of overland travel distance, was a calculation of the circumference of the entire Earth, and it came astonishingly close to the true value, arrived at more than 17 centuries before anyone would circumnavigate the globe to confirm it directly. It stands as one of the earliest and most beautiful examples of a principle that would go on to define essentially the entire subsequent history of humanity's effort to measure the cosmos, that with sufficiently clever geometric reasoning, careful measurement of angles, and a willingness to trust mathematics even when it describes something too vast to directly perceive, it becomes possible to measure distances far beyond anything a person could physically walk, sail, or otherwise traverse. The same essential technique, measuring subtle angles and applying careful geometry, would, many centuries later, become the foundation for measuring the distances to the stars themselves. The method is called parallax, and it relies on an effect anyone can observe directly with their own two eyes, without any specialized equipment at all, holding a finger up at arm's length, closing one eye and then the other, alternating back and forth, reveals the finger appearing to shift position relative to the more distant background behind it. This apparent shift is parallax, and it occurs because the two eyes observe the finger from two slightly different vantage points, separated by the width of the face. Astronomers realize that the Earth, in the course of its yearly orbit around the Sun, provides two vantage points separated not by a few centimeters, as with human eyes, but by roughly 300 million kilometers, the diameter of Earth's orbital path. By carefully measuring the tiny apparent shift in a nearby star's position against the backdrop of much more distant stars, observed 6 months apart, when the Earth occupies opposite sides of its orbit, astronomers can use exactly the same geometric principle Eratosthenes used with his shadow to calculate the actual physical distance to that star. This technique, first successfully applied in the 1830s by the astronomer Friedrich Bessel, opened the door to measuring stellar distances directly for the first time in human history, rather than merely estimating them through indirect, unreliable methods. But parallax, however elegant, has a hard practical limit. The angles involved become so vanishingly small for sufficiently distant stars that even the most precise instruments eventually lose the ability to measure them reliably, which restricts direct parallax measurements to stars within a few thousand light years, a remarkable achievement in its own right, but a vanishingly small fraction of the distances involved in mapping the observable universe, which extends billions upon billions of times farther. To measure genuinely cosmic distances, the distances to other galaxies, and eventually to the very edge of the observable universe, astronomers needed an entirely different technique, one that did not rely on measuring tiny angular shifts at all. This technique emerged from one of the more unexpected corners of astronomical research, the careful, painstaking study of a particular class of pulsating stars called Cepheid variables, whose brightness rises and falls in a remarkably regular, periodic pattern. An astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory in the early years of the 20th century, made a discovery while cataloging thousands of these variable stars that would prove to be one of the single most consequential findings in the entire history of astronomy, even though her name remains far less widely known than it deserves. Leavitt noticed a precise, mathematically clean relationship between the period of a Cepheid variable's pulsation, how many days it took to complete one full cycle of brightening and dimming, and its intrinsic brightness, the actual amount of light it was producing, independent of how far away it happened to be from Earth. Stars that pulsed more slowly were, without exception, intrinsically brighter than stars that pulsed more quickly, and the relationship between period and brightness followed a precise, predictable mathematical curve. This discovery provided astronomers with something extraordinarily valuable, a reliable way to determine a star's true, intrinsic brightness simply by timing its pulsation period, with no need to already know its distance. And once a star's true intrinsic brightness is known, comparing that to how bright it actually appears from Earth, which naturally diminishes with distance according to a well-understood mathematical relationship, the same way a lit candle appears dimmer the farther away it is held, allows the distance to that star to be calculated directly. Astronomers began calling such objects standard candles, because, much like a candle of known, standardized brightness, they provide a fixed reference point from which distance can be reliably calculated. Cepheid variables can be identified and measured at distances far beyond anything parallax could ever hope to reach, extending the reach of astronomical distance measurement from a few thousand light years out to tens of millions of light years, encompassing not merely individual stars within our own galaxy but entire other galaxies altogether. It was, in fact, precisely this technique, measuring Cepheid variable stars within a smudge of light then known simply as the Andromeda Nebula, that allowed the astronomer Edwin Hubble, in the 1920s, to demonstrate conclusively, for the first time in human history, that this particular smudge of light was not a nearby cloud of gas within our own galaxy, as many astronomers of the era had assumed, but was in fact an entirely separate galaxy, located roughly 2.5 million light years away, containing hundreds of billions of stars of its own. This single measurement, made possible by Leavitt's earlier discovery of the period-brightness relationship, fundamentally and permanently expanded humanity's understanding of the scale of the universe, revealing for the first time that our own Milky Way, previously assumed by many to constitute essentially the entirety of existence, was merely one galaxy among what would eventually prove to be hundreds of billions. Even standard candles, however, eventually reach their own limit. Individual stars, even unusually bright ones, simply become too faint to reliably detect at the truly staggering distances involved in mapping the outer reaches of the observable universe. For these most extreme distances, astronomers turn to an even more extreme and more luminous standard candle, a specific, well-understood category of stellar explosion called a Type Ia supernova, produced under very particular physical conditions involving a dense stellar remnant called a white dwarf slowly accumulating additional mass from a companion star until it crosses a precise physical threshold, triggering a runaway thermonuclear explosion of remarkably consistent, predictable intensity across every known instance of the phenomenon, regardless of which specific star or galaxy happens to produce it. Because these explosions release such a staggeringly, reliably consistent amount of energy, briefly outshining the combined light of every other star in their host galaxy, they remain detectable and precisely measurable across distances of billions of light years, providing exactly the tool needed to measure the very outer reaches of the observable cosmos. It was, in fact, the careful study of these extraordinarily distant Type Ia supernova explosions, carried out by two independent international research teams in the late 1990s, that produced one of the single most surprising and consequential discoveries in the entire history of cosmology. The finding, published in 1998, that the expansion of the universe is not merely continuing, as had been understood since Hubble's original discovery decades earlier, but is actually accelerating, speeding up over cosmic time rather than gradually slowing down under the gravitational pull of all the matter it contains, as most physicists of the era had confidently expected. This discovery, which earned its principal researchers the Nobel Prize in Physics in 2011, fundamentally reshaped every subsequent discussion of the universe's ultimate fate, and it is, quite directly, the very same accelerating expansion responsible for the causal horizon, the eternal inflation, and the eventual heat death discussed at length earlier in this exploration. Without those precise, painstaking supernova measurements, extending a chain of techniques stretching back, in an unbroken methodological lineage, to a scholar measuring shadows in ancient Alexandria, none of the questions explored throughout this piece could even properly be asked, let alone meaningfully addressed. It is worth holding on to this history, if only briefly, because it offers something valuable amid all the staggering, almost dizzying scales discussed throughout this exploration. A reminder that every single number cited here, every billion light years, every reference to an accelerating expansion, every claim about the age or shape or ultimate fate of the cosmos, traces back, through an unbroken chain of careful observation, patient measurement, and rigorous mathematical reasoning, to human beings, working with the tools available to their particular era, looking carefully at the world and asking, again and again, across more than 2,000 years, how big, exactly, is all of this? And, again and again, the answer has turned out to be larger, stranger, and more genuinely wonder-inducing than whatever came before it. There is a particular kind of scientific detective work worth examining more closely, because it represents the actual, ongoing, present-tense effort to answer the very question this exploration has been circling from every possible angle, not through pure theory, not through elegant analogy, but through the exhausting, meticulous business of searching for physical evidence, hidden in plain sight, within data we have already collected. Return once more to the cosmic microwave background, the ancient afterglow of the early universe that has already done so much work throughout this exploration, from measuring the overall flatness of space to constraining the timeline of cosmic history. This faint microwave radiation, arriving from every direction of the sky in nearly equal measure, represents the single most information-dense relic available from the universe's infancy, and cosmologists have spent decades developing increasingly sophisticated ways of extracting every possible fragment of meaning from its subtle patterns. One particular line of investigation deserves special attention here, because it represents perhaps the most direct, most literal attempt yet undertaken to detect the actual global shape of the universe, not by inferring it indirectly from measurements of curvature, as described earlier, but by searching for a specific, distinctive signature that a finite, closed universe with an unusual topology might be expected to leave behind. This connects back to the earlier discussion distinguishing curvature from topology, the observation that even a perfectly flat universe, with zero measurable curvature in the traditional geometric sense, could nonetheless be finite if it possessed some kind of unusual connectivity, the video game-style wraparound structure where traveling far enough in one direction returns a traveler to their starting point, not because space is curved like the surface of a sphere, but because of some deeper, more exotic topological structure stitching space together in a way ordinary geometry alone cannot capture. If the universe genuinely possesses this kind of finite, wraparound topology, there is a striking, testable consequence that follows directly from it, and it involves nothing more exotic than light traveling in more than one direction to reach the same destination. In an infinite, simply connected universe, the kind most people intuitively imagine, light from any given source travels toward an observer along exactly one path, the most direct route available. But in a finite universe with a wraparound topology, light from a sufficiently distant, sufficiently bright source could, in principle, reach an observer by traveling in multiple different directions simultaneously, each path wrapping around the finite universe a different number of times before arriving, the way a sound made in a sufficiently reverberant room might reach a listener's ear multiple times, once directly and again, slightly delayed, after bouncing off a distant wall. If this were happening on a cosmic scale, it would produce a genuinely remarkable and detectable effect. The same distant object, or in the specific case of the cosmic microwave background, the same distinctive pattern of temperature fluctuations, would appear to show up more than once in the sky, in different apparent locations, having reached us along multiple distinct paths around a finite, wrapped universe. Cosmologists have described this predicted effect using a memorable phrase: if the universe is finite in this particular way, the pattern of the cosmic microwave background should contain matching circles, pairs of circular regions on opposite sides of the sky, whose temperature fluctuation patterns match one another with unusual, statistically significant precision, evidence that we are looking at the same underlying region of space, its light having wrapped around the finite cosmos to reach us from two different apparent directions. Beginning in the early 2000s, following the release of increasingly detailed, increasingly precise satellite maps of the cosmic microwave background, several research teams undertook exactly this search, combing through the data for any statistically significant sign of these matching circles. The search has, to date, come back negative. No convincing evidence of matching circle pairs has been found in any dataset examined so far, a result generally interpreted as placing a strong lower limit on how small any wraparound topology could possibly be, if it exists at all. If the universe does possess this kind of finite structure, the scale of that structure must be significantly larger than our current observable horizon, meaning any evidence of it would require light to have completed at least one full circuit of the cosmos within the roughly 13.8 billion years available since the beginning. And if the universe's true scale exceeds that circuit distance, no such evidence could possibly exist within currently observable data, regardless of whether the underlying topology is genuinely finite or not. This is a sobering, important lesson embedded within an otherwise highly technical search, and it applies with equal force to every single one of the major possibilities explored throughout this piece. Some questions about the ultimate shape and extent of the universe may not merely be currently unanswered, but may be permanently, physically unanswerable, not due to any limitation of human ingenuity or technological capability, but due to the fundamental, unavoidable limitation imposed by the finite speed of light interacting with the finite time that has elapsed since the beginning of everything. If the universe wraps around on a scale larger than our particle horizon allows light to have traveled, we may never, under any conceivable future improvement in instrumentation, be able to detect that wraparound directly, not because our telescopes aren't good enough, but because the relevant light simply has not had time to complete its journey and reach us yet, and depending on the accelerating expansion of space, in some scenarios discussed earlier, it may never have that opportunity at all. There is a separate, ongoing puzzle within cosmic microwave background research worth mentioning as well, because it illustrates something valuable about the current, genuinely unsettled state of observational cosmology, rather than presenting a picture of a field with every important question already neatly resolved. Careful statistical analysis of the detailed patterns within the cosmic microwave background has revealed a small number of curious, statistically modest anomalies, subtle features in the data that do not perfectly match the predictions of the simplest, most widely accepted cosmological models, including unexpectedly low levels of fluctuation at the very largest observable scales, and a curious apparent alignment between certain large-scale features that some researchers have, only half jokingly, nicknamed the axis of evil, given how thoroughly it seems to defy the expectation that the universe should look statistically uniform in every direction, with no preferred axis or orientation whatsoever. These anomalies remain a subject of genuine scientific debate. Some cosmologists regard them as likely statistical flukes, the kind of modest, occasional deviation from perfect uniformity that ordinary statistical variation would be expected to produce even within a genuinely uniform, isotropic universe, given that we are, after all, examining a single dataset drawn from a single observable universe, rather than being able to repeat the experiment across many independent universes to check whether the anomaly persists. Others regard these anomalies as potentially meaningful hints of new physics, possibly connected to the very questions of large-scale topology and geometry explored throughout this piece, though no consensus explanation has yet emerged. and it remains entirely possible that improved future data, from missions still being planned and built, will resolve these anomalies definitively in one direction or the other, or that they will persist as a genuine, unresolved mystery for a considerable time to come. It is worth pausing on this honestly, rather than rushing past it toward a tidier conclusion, because it captures something essential about the actual character of frontier science, as distinct from the neatly packaged, fully resolved version of scientific knowledge that often gets presented in popular explanations. The question of the edge of the universe is not a settled matter awaiting only a final, confirming press release. It is an active, ongoing, sometimes frustrating, often exhilarating area of genuine research, populated by working scientists who spend their careers carefully searching through faint patterns in ancient radiation, cross-checking statistical anomalies against one another, building increasingly sensitive instruments, and slowly, patiently narrowing the space of possible answers, one painstaking measurement at a time, fully aware that a definitive, final answer may not arrive within their own lifetimes, and might, given the physical limitations discussed throughout this piece, never arrive at all. And yet the search continues, not despite this uncertainty, but in many ways because of it. There is a particular kind of intellectual courage embedded in the willingness to spend an entire career investigating a question that may never yield a complete, satisfying answer, a willingness to treat the incremental narrowing of possibility, the careful ruling out of alternatives, the patient accumulation of ever more precise constraints, as a worthy and meaningful form of progress in its own right, even in the absence of the kind of clean, final resolution that popular imagination often expects from science. This, perhaps as much as any specific finding about curvature or expansion or topology, represents one of the deepest lessons embedded within the entire history of humanity's effort to understand the edge, or the edgelessness, of everything that exists. Step back now from the technical detail of horizons and topologies and landscapes, and consider, for a moment, the peculiar position occupied by the mind attempting to hold all of this together, because there is something worth examining honestly about why this particular question, more than almost any other in science, produces such a distinctive, persistent kind of vertigo. Human cognition did not evolve to comprehend distances measured in billions of light years, or timescales measured in numbers so large that scientific notation becomes not merely convenient but strictly necessary, since ordinary decimal notation would require more digits than could reasonably be written out and read. Every cognitive tool available to the human mind for estimating size, distance, and quantity was shaped by an evolutionary environment consisting of savannas, forests, watering holes, and the immediate, pressing concerns of finding food, avoiding predators, and navigating a social world measured in dozens, perhaps low hundreds, of other individuals. The largest natural quantities our ancestors regularly needed to estimate were things like the size of a herd of animals visible on a distant plain, or the number of days until a particular season arrived. Nothing in that evolutionary context prepared the human brain to intuitively grasp the difference between a million and a billion, let alone the difference between 46 billion light-years and the genuinely, mathematically infinite extent proposed by some of the models discussed throughout this piece. This is not a flaw or a failure of human intelligence. It is simply a mismatch of scale, the same kind of mismatch that makes it genuinely difficult for most people to intuitively grasp the true relative sizes and distances within our own solar system, despite that system being almost inconceivably smaller than the scales discussed throughout this exploration. Consider, briefly, a simple thought experiment frequently used by science educators to illustrate this very mismatch. If the Sun was shrunk down to the size of a large beach ball, roughly a meter across, the Earth, on the same scale, would be a small marble, a little over a centimeter in diameter, orbiting that beach ball at a distance of over 100 meters away, roughly the length of a football field. Neptune, the outermost major planet, would be a smaller marble still, orbiting at a distance of over 3 kilometers from the beach ball Sun. And even at this dramatically compressed scale, the nearest star beyond our own Sun would still be located over 28,000 kilometers away, more than half the actual physical circumference of the real Earth. This is merely the distance to the nearest star. It says nothing yet about the distance across our own galaxy, let alone the distance to other galaxies, let alone the radius of the entire observable universe. Most people, encountering this thought experiment for the first time, report a genuine, visceral shift in perspective, not merely an intellectual acknowledgement that space is large, which everyone already nominally knows, but something closer to an emotional recalibration, a felt sense of just how staggeringly, almost violently empty even our own comparatively cozy corner of the universe actually is. And this recalibration, striking as it is, describes only the scale of our own solar system relative to the nearest handful of neighboring stars. It says nothing yet about the roughly 100 billion to 400 billion stars estimated to populate our own galaxy alone, nor about the hundreds of billions of additional galaxies, each containing their own comparable populations of stars, currently estimated to exist within just the observable portion of the universe, to say nothing of whatever portion, finite or infinite, lies beyond that observable horizon. There is a particular kind of humility that emerges from sitting with these numbers honestly, rather than allowing them to simply wash over the mind as abstract, ultimately meaningless quantities too large to hold any real emotional weight. It is a humility not born of despair or insignificance, though it is easy to see how someone might initially interpret it that way, but something closer to the humility experienced by a person standing at the edge of a genuinely enormous canyon for the first time, confronted directly, physically, undeniably with a scale of geological time and geological process that dwarfs, without diminishing, the significance of their own individual life and concerns. This comparison is worth extending slightly further, because it captures something important about the appropriate emotional register for engaging with cosmological scale. Standing at the edge of a vast canyon does not typically make a thoughtful visitor feel that their own life is worthless or meaningless by comparison. It tends, instead, to produce something closer to, or in its most technically precise psychological sense, a specific emotional state, studied directly by researchers in the field of positive psychology, characterized by two core components: a perception of vastness, something significantly larger than the self or the self's ordinary frame of reference, combined with a need for cognitive accommodation, a sense that existing mental frameworks must stretch, expand, or reorganize themselves in order to make sense of what is being encountered. This particular emotional state has been linked, in a growing body of psychological research, not to feelings of insignificance or despair, but to measurably increased feelings of connectedness to something larger than oneself, increased generosity toward others, and a broadened, more expansive sense of time itself, in which the ordinary, pressing concerns of daily life temporarily recede in favor of a wider, more patient perspective. The question of the edge of the universe, approached honestly, produces precisely this kind of awe, and it is worth acknowledging directly that this emotional response is not a distraction from the scientific content, some kind of sentimental decoration layered on top of the real physics, but is, in fact, an entirely appropriate and arguably essential response to genuinely, accurately comprehending what the science actually describes. A person who learns that light from the most distant visible galaxies has been traveling for over 13 billion years, that the object which emitted that light has since receded to a distance the light itself never actually crossed, that entire regions of space are, at this very moment, permanently and irreversibly vanishing beyond any possible future contact due to the accelerating stretch of space itself, and yet somehow does not feel even a flicker of genuine astonishment, has probably not yet fully absorbed what these facts actually mean, however fluently they might be able to recite the relevant numbers. There is also something valuable, something almost unexpectedly consoling, embedded within the very structure of the uncertainty explored throughout this piece, the fact that we do not yet know, with final certainty, which of the four major possibilities correctly describes the true shape and extent of the cosmos. It would be entirely reasonable to expect that this uncertainty should produce frustration, or a diminished sense of scientific achievement, given how much effort, across so many centuries and so many brilliant individual contributions, has gone into narrowing down the possibilities this far. And yet there is a different, equally valid way of experiencing this same uncertainty, as an invitation, rather than a deficiency. Every one of the four possibilities explored throughout this piece remains, at the time of this recording, a live, mathematically serious, actively studied option, each one supported by real physics, each one carrying genuinely different implications for the ultimate nature and fate of everything that exists, and each one, crucially, still capable of being refined, tested, or ruled out by future observation, future instruments, future generations of researchers building on the patient, unbroken chain of measurement stretching back to a scholar with a shadow stick in ancient Alexandria. This is, in its own way, a genuinely privileged position to occupy, historically speaking. Every generation of astronomers throughout human history has necessarily worked at the edge of their own era's particular ignorance, confidently asserting cosmological pictures that later generations would go on to dramatically revise, overturn, or entirely discard. The crystalline celestial spheres of Aristotle, the Earth-centered universe defended for so many centuries afterward, the assumption of a static, eternal, unchanging cosmos that persisted right up until Hubble's observations in the 1920s forced its abandonment. There is no particular reason to believe the current era represents some kind of final exception to this long historical pattern, some privileged moment in which humanity has finally arrived at the complete, unrevisable truth about the shape and extent of everything. It is entirely possible, perhaps even likely, that some future generation, equipped with instruments and theoretical frameworks not yet developed, will look back on the four possibilities carefully explored throughout this piece and recognize elements of truth scattered among more than one of them, or will discover some entirely different, currently unimagined fifth possibility that reframes the entire question in ways impossible to anticipate from the vantage point of the present. And this, perhaps, is the appropriate note on which to approach the final synthesis of everything explored throughout this piece, not as a search for a single, final, triumphant answer that resolves all remaining uncertainty, but as a genuine, ongoing act of collective intellectual courage, an entire species, confined for the whole of its existence to a single small planet orbiting a single unremarkable star, nonetheless reaching, through nothing more than careful observation, patient mathematics, and an apparently inexhaustible curiosity, toward an understanding of scale so vast, so far beyond anything directly experienced by any individual human life, that the very act of asking the question honestly requires a kind of sustained intellectual humility rarely demanded by any other pursuit available to human beings. Gather now everything explored throughout this piece and lay it side by side, the way a detective might spread out every piece of evidence collected across a long, difficult investigation, searching for the pattern that connects them. There is the lantern in the dark field, the simple, almost embarrassingly straightforward realization that the boundary of what we can see, our 46 billion light-year observable horizon, is not the boundary of what exists, but merely the boundary of what light has had time to show us since the beginning of everything. This is not speculation. This is confirmed, foundational physics, understood with total confidence by every working cosmologist, and it dissolves, on its own, the naive popular image of the universe as some kind of finite bubble of matter surrounded by a wall of nothingness. Whatever else may be true about the ultimate shape of the cosmos, this much is certain: the edge of our vision is not the edge of reality. There is the ant on the globe, the elegant, mathematically rigorous possibility that space itself curves back upon itself in some higher dimension we cannot directly perceive, producing a universe that is finite in extent, precisely measurable in principle, and yet utterly without a boundary anywhere within it. A cosmos where a sufficiently patient traveler moving in a perfectly straight line would eventually return to their point of departure, having circumnavigated the whole of existence, without ever once encountering a wall. Current measurements suggest this may not, in fact, describe our particular universe, or if it does, the curvature involved is subtle enough to remain undetectable across even our vast observable horizon. But the possibility remains alive, remains mathematically serious, and remains, regardless of its ultimate truth or falsehood regarding our specific cosmos, one of the most genuinely mind-expanding demonstrations available anywhere in physics of just how thoroughly our intuitions about space, shaped entirely by a lifetime spent on the surface of one small, flat-seeming planet, can fail to capture the true range of possibilities the mathematics of curved space actually permits. There is the boiling pot and the eternally inflating field, the sober, well-motivated possibility that our entire observable universe represents nothing more than a single, localized, cooled pocket within an unimaginably larger, still raging ocean of raw cosmic inflation, a possibility that transforms the question of an edge from a spatial question into a question about phase transitions, about the boundary between settled structure and endlessly generative chaos. This possibility carries with it the genuinely humbling implication that our entire 46 billion light-year sphere, everything we have ever observed, everything every telescope humanity has ever built has ever detected, might constitute only the tiniest, most parochial fragment of a whole so vast that our observable universe, relative to it, would be smaller by comparison than a single atom is relative to the size of the Earth. And there is the boiling pot stranger cousin, the multiverse, the landscape of string theory, the bubble universes separated by brands across which the fundamental laws of physics themselves might not carry over, an edge not merely of space or of causality but of the rulebook governing reality itself. This remains the most speculative, the most contested, the most philosophically fraught of the four possibilities, sitting uncomfortably close to the boundary between rigorous theoretical physics and something that even some of its own proponents acknowledge risks drifting into unfalsifiable territory. And yet it emerges, not from idle speculation, but from some of the most carefully developed mathematical frameworks in contemporary theoretical physics, frameworks originally built to solve entirely different, well-motivated problems, only to find this staggering implication arriving, uninvited but seemingly unavoidable, as part of the package. Four possibilities. For fundamentally different shapes for the ultimate boundary, or lack thereof, of everything that exists. And running quietly underneath all four, present regardless of which one, if any, turns out to correspond to physical reality, is the thermodynamic thread explored separately, the slow, patient, utterly reliable arithmetic of entropy, ensuring that whatever the true spatial extent of the cosmos turns out to be, its capacity for structure, for order, for anything resembling an event worth recording, is not eternal, but is instead a finite inheritance, being spent, star by star, galaxy by galaxy. At a rate we can calculate with reasonable confidence, tracing an arc toward an eventual state of stillness so complete that the very concept of a meaningful edge may, by that point, have become as irrelevant as the concept of a meaningful event. What, then, should be made of all this, not as a matter of physics, which has already been treated as carefully and as honestly as space allows, but as a matter of simple human perspective, the perspective of a single mind, on a single planet, attempting to hold the whole of this picture together at once. Consider, one final time, the image of the mirror maze, a structure familiar to anyone who has ever wandered through one at a fair or an amusement park, walls of reflective glass arranged at careful angles, producing an environment in which every direction appears to extend into infinite, receding repetitions of the same corridor, the same reflected figure, stretching backward and forward without any visible end. A person standing inside such a maze, holding nothing more than a single small light, faces a genuinely difficult epistemic problem. How can they determine the true size and shape of the space they occupy, when every wall they can see is, in some sense, not a true boundary at all, but a reflection, a repetition, a distortion of information bouncing back and forth in ways that make direct visual assessment of the maze's actual physical dimensions essentially impossible from the inside? And yet, and this is the crucial point, the point on which this entire exploration ultimately rests, a person trapped inside such a maze is not, in fact, helpless. They cannot simply look around and directly perceive the maze's true shape, the way they might assess the size of an ordinary, non-reflective room with a single sweeping glance. But they can do something else, something that turns out, upon careful examination, to be even more powerful than simple direct observation. They can reach out and touch the glass. They can measure the angle at which light bends and reflects off each surface. They can carefully track how their own reflection appears to move as they shift position, extracting, through careful geometric reasoning applied to indirect evidence, information about the maze's true structure that direct, naive observation alone could never provide. This, in the most literal sense achievable within the constraints of a single essay, is precisely the situation in which human cosmology finds itself, and has always found itself, throughout the entire history explored across this piece. We cannot simply look out at the universe and directly perceive its true, total shape and extent, the way we might glance around an ordinary room and immediately grasp its dimensions. Every photon of light reaching any telescope on Earth arrives already carrying the accumulated distortions of billions of years of travel through an expanding, evolving cosmos, showing us not the present but a deep, layered accumulation of the past, stretched and reddened by the very expansion we are attempting to measure. And yet, exactly like the person in the mirror maze reaching out to touch the glass, human cosmologists have not remained passive before this apparent limitation. They have measured the angle of ancient shadows in Alexandria. They have tracked the subtle parallax shift of nearby stars against the fixed backdrop of more distant ones. They have catalogued the precise, predictable pulsation of variable stars across other galaxies entirely. They have calibrated the reliable, explosive brightness of dying stellar remnants across billions of light years. They have measured, to a precision of a fraction of a percent, the subtle curvature, or absence of curvature, encoded within the faint microwave afterglow of the universe's earliest moments. They have searched, so far without success, for matching circles that would betray a hidden, finite, wraparound topology. And they have built, from all of this patient, accumulated indirect evidence, an increasingly precise, increasingly confident, if still genuinely incomplete, picture of the true shape of the maze they find themselves inside. There is no shame, and there should be no frustration, in the fact that this picture remains incomplete. It would be a strange, almost suspicious thing if a single species, working for barely more than a few centuries with modern scientific method, confined for the entirety of that effort to a single small planet, had somehow already arrived at the final, complete, unrevisable truth about the total shape and extent of all existence. What should be remarkable, what genuinely deserves to be treated as one of the great, quietly astonishing achievements of the entire human intellectual project, is not that the question remains open, but that it has been narrowed at all, narrowed from an ancient world in which the ceiling of existence was confidently imagined as a solid dome studded with fixed lights, to a modern world in which four distinct, mathematically rigorous, observationally constrained possibilities remain on the table, each one representing not ignorance but the outer edge of genuine, hard-won knowledge, each one capable, in principle, of being further tested, refined, or eliminated by future generations building on exactly the same patient, evidence-based methodology traced throughout this piece, back to a scholar and a shadow stick in ancient Alexandria. The edge of the universe, whatever its true nature ultimately proves to be, is not merely a physical boundary waiting somewhere out in the depths of space to be finally reached by some sufficiently advanced future spacecraft. It is, in an equally real and perhaps more immediately meaningful sense, the current outer boundary of human understanding itself, a boundary that has moved, dramatically and repeatedly, across the whole of recorded history, and shows no particular sign of having permanently stopped moving now. Every one of the four possibilities explored throughout this piece represents not a final wall against which human curiosity has helplessly crashed, but a genuine frontier, a place where the light of current knowledge fades into the darkness of the not yet known, in exactly the same way the light of a single lantern fades into the darkness of an unmeasured field. And perhaps this, in the end, is the most honest and most genuinely satisfying answer available to the original question. What lies at the edge of the universe is not, and was perhaps never going to be, a simple physical thing waiting to be discovered and described in a single sentence, the way one might describe the far shore of a lake or the outer wall of a house. It is something closer to a living frontier, a boundary defined jointly by the physical structure of reality itself and by the current, ever-expanding reach of a curious species willing to spend its entire intellectual history reaching for it. Every generation that has ever asked this question has pushed that frontier further outward, has redrawn the boundary of the known a little farther into the darkness, using nothing more than careful observation, patient mathematics, and the same fundamental willingness to trust reason over comfortable intuition that first allowed a scholar in Alexandria to measure the size of an entire planet using nothing more than a stick, a shadow, and the confidence to believe that the universe, however vast, was not beyond the reach of a sufficiently careful mind willing to measure it. That willingness has not diminished. If anything, equipped now with satellites orbiting far above the atmosphere, with instruments capable of detecting temperature variations in ancient radiation smaller than a millionth of a degree, with a century of accumulated theoretical physics stretching from Einstein's equations to the string theory landscape, it has only grown more capable, more ambitious, more precisely targeted at exactly the deepest, hardest, most genuinely unresolved questions explored throughout this piece. The edge of the universe remains, for now, unreached, unresolved, genuinely uncertain in its final nature. But it is not, and has never been, unreachable in principle, only unreached, for now, by a species that has already, in the astonishingly brief span of a few thousand years, measured the size of its own planet, mapped the structure of its own galaxy, traced the expansion history of the entire observable cosmos back to its first fraction of a second, and is still, at this very moment, somewhere on Earth, quietly, patiently, continuing to look up, continuing to measure, continuing to ask the question this entire exploration has been built around, not because the answer has already been found, but precisely because it has not, and because the search itself, incomplete as it remains, has already proven itself to be one of the most genuinely worthwhile pursuits any curious mind, on any small planet, orbiting any unremarkable star, could ever choose to undertake.